So we're still in section 6.2 if we're trying to match things up with the book. But today and next time, we're going to look at what we call volumes of solids with known cross-sections. As opposed to spinning things around an axis, I'm going to tell you some information about cross-sections of a solid, and then we're going to try to find the volume. For our first example, the region bounded by the parabola y equals 4 minus x squared, and the x-axis is the base of a solid. For this particular solid, each cross-section perpendicular to the x-axis is a square. We want to find the volume of this solid that we've created. You might want to pause the video for a moment while you copy that down. Before we do anything with this, we should draw this region that's being discussed. So let's see, 4 minus x squared. Yes, you can use a calculator, although I think we kind of should know what that's going to look like. The parabola is going to be, let's see, something like this, and bound by the x-axis as well. So this thing over here is the base of our region. We're told that cross-sections perpendicular to the x-axis are squares. Well, here's the deal. That line that I just drew in is the base of a square that is coming out of the paper towards you. And here's the base of another square. The base is bigger, and because it's a square, that means it's going to come out further towards you. And here's another base, and another base, and another base. And all those lines are bases of squares that come out of the xy plane. I feel like this probably doesn't make a whole lot of sense right now, so I need to show you a better demonstration of what exactly this solid looks like. So, here's the base of our region. This is that 4 minus x squared parabola. That's our region bounded by the parabola and the x-axis. And here is one of those squares that I was talking about. The base is in the xy plane, and the base is perpendicular to the x-axis, and it's sticking up out of the page. I can put the square somewhere else. Maybe the square is over here, or over there, or over there, or over there, or any of those places. All of these squares are cross-sections of our solid. Actually, they're not really squares. Squares are two-dimensional things. These are really square prisms. It's a square with a very small thickness to make it a three-dimensional thing. All those squares together are creating our solid. What does the solid itself actually look like, not just the individual squares? Well, something like this. And each of the cross-sections, if you slice this thing perpendicular to the x-axis, will be squares. It's still going. So now that you've seen what this solid looks like, we need to talk about how to find the volume of this thing. To find the volume, well, the first thing we're going to do is we're going to find the area of one of those squares, whose base is perpendicular to the x-axis. We're going to find the area of one of the squares. However, the shapes aren't actually squares, they're actually prisms with a very, very small thickness that we'll call delta x or delta y, or from our calculus perspective, dx or dy. Each is actually a prism with a thickness of delta x or delta y, or dx or dy, one of those things. So we're going to find the area of a square and really turn that into a volume thing because it's really a prism with a very small thickness. That will just be one of the prisms, though. I really have infinitely many prisms, infinitesimally thick, and I'm going to add up all those volumes by just taking an integral. Add up all the volumes with an integral. Our volume is just going to be the integral from a to b of the area of one of our squares, dx, times the thickness of that square. So, let's take a look at one of those squares. I'm going to draw out a square over here. I'll put some markings in there. The base of the square, this thing over here, is one of those lines over there. I just need to figure out the height of that line, and that height of the line will correspond to the base of the square. Well, what's the height of the line? What's the height of this little strip? Or like we could even call it a representative rectangle. Well, we can do what we were doing with our solids of revolution and just do the top function minus the bottom function. Our parabola minus the x-axis, 4 minus x squared minus 0, or really in this case just 4 minus x squared. The base of that square is the height of one of these strips, which is just, well, 4 minus x squared. What's the height of your square over here? Well, it's a square. So the height and the base have to be the same thing. I'm going to say that's 4 minus x squared. The area of one of those squares is going to be 4 minus x squared squared. That will find the area of one of those squares. How do I add them all up? I'm going to take an integral. The volume is going to be the integral, well, over the region that I'm dealing with. The x values for my region start from -2 and end at +2. So I'm going to integrate from -2 to +2, and I'm going to integrate that area formula, 4 minus x squared squared dx, the thickness, which turns our two-dimensional area into a three-dimensional volume. Add up all those volumes with a very small thickness. You're going to want to just go to the calculator and do the integral in the calculator, although you could FOIL the thing out and do your antiderivatives. Go to the calculator and go do your FN int stuff. And when you do that, that should give you a volume of 512/15 for that solid that we took a look at. I don't know if this is actually going to work, but last year, at the end of the year, I had 2 juniors left in the class, and we had about a month to go after the seniors left. And what we did was we spent some time working with some of the equipment from the makerspace to actually create some of these solids. Not sure if you're actually going to be able to see this very well. But that thing, yeah, you really can't see that well with the document camera. But this thing has a base. That's our parabola. Cross-sections perpendicular to the x-axis are squares. So if I slice this over there, I get a bunch of squares. And this is kind of the solid that we were just talking about. Let's take a look at a couple other problems. Next example. I am going to redo the last problem. But I'm going to change the shape of the cross-sections. So now I'm going to do this where the cross-sections perpendicular to the x-axis are, well, I'm going to start by dealing with right isosceles triangles with a leg in the xy plane. write isosceles triangles with a leg in the xy plane. I promise that sounds more complicated than it actually is. I want a right triangle. Right triangle. Isosceles, which means two of the sides are equal. The leg, that's the thing in the xy plane. So if I go back to my region from the previous problem, that vertical line matches up with the base of one of the triangles. Before we go on, I think we should take a look at what this is going to look like. So again, we have our region bound by the parabola and the x-axis, and now the cross-sections are those triangles that we talked about. So here's one of the triangles, and I can sort of slide this along the x-axis. You can see a whole bunch of different cross-sections. Again, they're not really triangles, they're triangular prisms, triangles with a very small thickness. And if I go and create the solid, my entire solid is going to look something like that. Maybe I should try to rotate this thing so you can see this a little bit better. Now I'm kind of messing with this, and that's not so helpful. Well, that's our solid. Well, the base of my triangle, one of those strips over there, and again, there are infinitely many of those things, is just the height of this strip that we see, which is 4 minus x squared. It's an isosceles triangle, so the height of the triangle is 4 minus x squared. Area, 1/2 base times height, 1/2 times 4 minus x squared times 4 minus x squared, or why don't we just say 1/2 times 4 minus x squared squared. Area of one of those triangles. Now to find the volume, I'm going to go and integrate over the x values in my region. I'm going to integrate from -2 to 2, 1/2 times 4 minus x squared squared dx. And I could go to the calculator at this point, but there's going to be an easier way to do this problem. I'm going to take that 1/2 and I'm going to move it out front. And I'm going to say 1/2 times the integral from -2 to 2 of 4 minus x squared squared dx. Hopefully, maybe, that integral looks familiar to you. Because I think that's exactly what we did in the last problem. Oftentimes, with these problems, if we start by saying our cross-sections are squares, we can base other volumes on the volume when the cross-section is a square. According to that previous problem, I know that this thing over here is 512 over 15, so my volume is 1/2 times 512 over 15, or 256 over 15. I guess you don't have to do that. You can just go to the calculator and type it in, but maybe we can save a little bit of time. Let me try to show you the model of this one. Again, created last year using the 3D printer from the Makerspace. The base of this thing is my parabola. Cross-sections are triangles. If you slice this thing over there and there and there and there and there, you're going to get a whole bunch of triangles out of this thing. Part B. What if we're dealing with cross-sections that are semicircles? I'm going to draw a semicircle over here. Base of my semicircle is one of those strips that we saw over there. Let's take a look at what this solid looks like. So there's our base again. Our cross-section this time is a semicircle. Let me show you a couple of those semicircles. And I'm now going to try to create the solid. And it's looking something like that. Maybe that's not helping so much. Well, whatever. You get a sense of what this looks like. Well, the area of a semicircle is 1/2 pi r squared. I know that this entire base over here is 4 minus x squared, but that's not my radius. That's the diameter. The radius is half of that thing. So when I plug in this formula, I'm going to get 1/2 pi times 1/2 of 4 minus x squared, and I'm going to square that thing. This thing over here is my radius, half of the diameter, and then I'm going to square it. Let me do a little bit of cleaning up, a little bit of algebra over here. A equals 1/2 pi times square the 1/2, you get 1/4. Square that thing, you get 4 minus x squared in parentheses squared. Do not distribute the square, you'd need to FOIL if we were going to do that, and I'm not going to bother. And I can say that my area is pi over 8 times 4 minus x squared squared. To find the volume of the entire solid, I'm going to integrate over the x values of my region. So integrate from -2 to +2. Pi over 8 times 4 minus x squared squared dx. Like the last problem, I can take the pi over 8 up front. B equals pi over 8 times the integral from -2 to 2 of 4 minus x squared squared dx. I can again take the value of the integral from the previous problem when we dealt with cross-sections that were squares. And I'm going to say pi over 8 times 512 over 15, which should give you 64 pi over 15. I do have a model for this one as well. Really not sure how well these show up, but again, bases are parabola. Cross-sections here are semicircles. If you slice this there and there and there and there and there, you'd get cross-sections that are going to look like semicircles. Okay, so I have one more example we're going to look at with 3 parts, and then that should do it for today. A solid has a base given by x squared plus y squared equals 1. I want to find the volume of the solid whose cross-sections perpendicular to the x-axis are, and we're going to start with squares. Solid has a base given by x squared plus y squared equals 1. I want to find the volume of the solid whose cross-sections perpendicular to the x-axis are. First, we're going to deal with squares. Well, I need to draw this base. You should remember from pre-calc that x squared plus y squared equals 1 is a circle. Circle with a center at the origin with a radius of 1. And it's going to look like that. And my cross-sections perpendicular to the x-axis are these things over here. And I want to deal with cross-sections that are squares. So I'm going to draw a square over there. And one of these strips over here is the base of our square. Should match up like that. Well, we've got a little bit of work to do to figure out the length of this base, the height of one of these strips. I'm going to take that x squared plus y squared equals 1, and I'm going to solve that for y. I need functions over here. I'm going to get y squared equals 1 minus x squared. I'm going to undo my square by doing the plus and minus square root of that thing. And the point is, the top half of this circle has a formula given by y equals the square root of 1 minus x squared. And the bottom half has a formula given by y equals negative the square root of 1 minus x squared. So what's the length of this strip, the length of the base? I need to just do the top function minus the bottom function. Same thing I did with area between two curves, or volumes of solids of revolution. The top minus bottom, well, in this case, is going to give me the square root of 1 minus x squared minus negative the square root of 1 minus x squared, or just 2 times the square root of 1 minus x squared. It's a square, so the height's going to be the same thing, 2 times the square root of 1 minus x squared, and the area is going to be 2 times the square root of 1 minus x squared, in parentheses, squared. I might as well simplify again here. I'm going to get 4 times square root. They cancel. 4 times 1 minus x squared. Maybe I'll just sort of leave it like that. My volume, now I'm going to integrate that area, dx, over the x values in my region. My region goes from an x value of negative 1 to an x value of positive 1. So I'm going to integrate from negative 1 to positive 1. 4 times 1 minus x squared dx. Go to the calculator and integrate this thing. Go do your FN int stuff. And I think that you should be able to get 16 thirds out of that. Before we go on, let's take a look at what this solid looks like, just for fun. So there's my base of a circle and one of those squares. And some more squares. And if I go and generate the entire solid, it'll look something like that. Next thing I want to deal with is what happens if the, part B, if the cross sections are rectangles with a height of 2. Rectangles with a height of 2. Well, I'm going to draw in a rectangle. Base of my rectangle matches with one of the strips over here. I already know that the height of one of those strips, the length of one of those strips, the base of my rectangle is going to be the same thing that it was from my square. Still going to be 2 times the square root of 1 minus x squared. The height is always 2. It's a constant 2. I didn't say the height was twice the base or something like that. That would be then 2 times 2 root 1 minus x squared. I said that the height is a constant of 2. So my area is going to be the base times the height, 2 times 2 root 1 minus x squared, or 4 root 1 minus x squared. To find the volume, I'm going to integrate this thing from negative 1 to 1. I'm going to do 4 times the square root of 1 minus x squared dx. And I don't think that we can base this one on what we had in part A. If it's the same thing other than a constant, I can mess with things, but here it's a different function inside, 1 minus x squared versus square root of 1 minus x squared. So go to your calculator, do your FN int, and I think it should actually be kind of an interesting number, and then we'll talk about what this is actually going to look like if you haven't already figured out what this is going to look like. It's going to take a little while because of the square root, but I think it should give you about 6.283186 or so on. That number look familiar? Well, let me show you what this looks like. Then we'll talk about what this number is and why I feel like this should actually make a whole lot of sense. Let's see. And now I can't find the stop button. Oh, there it is. Hold on. So again, there's the base. Here's one of our rectangles. Notice as I slide the rectangle, the height of that thing doesn't change. Height is always 2. Are you seeing that shape that's getting traced out? Were you picturing one of these things? Maybe? A cylinder? This number is just 2 pi. What's the volume of a cylinder? Volume of a cylinder, area of the base times how tall it is, pi r squared times the height. We had a cylinder that we saw in that demo with a radius of 1 and a height of 2. V equals pi times 1 squared times 2. Just 2 pi, following from that formula. I want to do one more variation of this. I'd like to end our notes today by looking at what happens if the cross-sections are semicircles. Try to picture this. I think I want to go through the calculations and then I'll show you what it looks like when we're done. So here's a semicircle. Base of the semicircle is, again, one of those strips that we were seeing over there. And I already know that the entire base has got to be 2 root 1 minus x squared. Area of a semicircle, 1/2 pi r squared. 1/2 pi. This is not the radius, that's the diameter. So the radius has to be half of that, which in this case actually isn't too bad. Radius is just square root of 1 minus x squared. So I'm going to do square root of 1 minus x squared. I'm going to square that. I'm going to clean this up a little bit. 1/2 pi times 1 minus x squared. My volume, I'm still going to integrate this thing from -1 to +1. I'm going to say pi over 2 times 1 minus x squared dx. I'm going to move my pi over 2 out front. And I'm going to get this. You could base this on part A if you want. You could also just go to the calculator, integrate this thing, divide your answer by 2 and tack a pi onto that. I think that's what I'm going to go do. And I think that should give you a volume of 2 pi over 3. Let's take a look at what this solid actually looks like. So there's one of our semicircles. Let me slide this and get a few more semicircles. And I can create the entire solid. It actually looks like half of the sphere. It's a hemisphere. We know that the volume of a sphere with a radius of 1 would be 4/3 pi times 1 cubed, or 4/3 pi, 4 pi over 3. This is half of that, so 2 pi over 3. So that's the basic idea of with these volumes of solids with known cross-sections. We're going to find the area of one of our shapes. We'll know the base of that shape by just kind of looking at the region that we're dealing with. And we'll figure out the top function minus the bottom function. That'll be our base. We're then going to add up all those areas, really not areas, really prisms with a very small thickness. I'm going to add them up by taking the integral over the x values in my region, and I'll get the volume. There's one final variation we need to look at, and we're going to save that for next time. And that will be, instead of looking at cross-sections perpendicular to the x-axis, we need to deal with cross-sections perpendicular to the y-axis. That is one tiny change. I think you might even be able to guess what that little change is, but we're going to deal with that next time.